This is the digital circuit class. And we're in chapter 12. And this is either the third or fourth day, maybe only the second day, I'm not sure. Probably only day 2. And we're going to start at section 12-6. Okay, so what we found out on the first set of computers that we made, we decided that lights would be perfectly okay and there's nothing wrong with them. We can have these lights coming on and off. And then the operator could figure out what the lights were trying to tell us. So that's trying to tell us 1, 1, 1, 1, which is a 15 or is an F, depending on how you look at it. And so we decided, after doing that for a little while, we decided that we need a better way to display the information the computer's doing. So you figure, what was the first application we used computers for that helped us out? Anybody know?
Oh, something military.
Yeah. Well, it had to do with the site tables. So there was a set of tables that you needed to do site reduction. If you're at sea, you'd pick a star and point at that star, and you could use that star to draw a line of position on your chart.
Sextant?
And, well, you'd have to use a sextant too. And then you'd use another star to do the same thing and draw another line. And if you used the third star, you could draw a third line. So if you had 3 lines crossing like that, you're inside the triangle someplace, maybe, if you did it quick enough. You'd have to take the sighting quick enough and go in there. But you needed a table that did the math for you in advance. And these tables were made 7 years in advance because ships would go to sea and leave England for 7 years and not come back. So they'd have to come back with them. And we needed them in World War II. We needed them in the Korean War. It wasn't until the early 60s where the idea of finding out where we are in the open ocean using the stars started going away, and we had Loran and we had Omega, and now we have GPS. We don't do it at all. But there was 1,000 mathematicians working on those tables, and it was a 12-volume set. And if you had that set, then you could go to sea and navigate the oceans blue, and that'd be fine. And if you didn't have that set, you better stay close to land because you're not going to know where you are. One of the first applications of a computer was to do that, and they made an entire set of site reduction tables in 30 minutes and fired the entire staff of mathematicians. Because once it was programmed to do the calculations that it had, it could do that. But clearly it couldn't have done that if the output was 1s and 0s in binary. Okay, the output had to be some other type of output that was reasonable to see. So we came up with this idea of a 7-segment display, and on the 7-segment display we could turn on, each of these are diodes, so you could think of them as each of them being a diode. And that means that on one side you have a cathode and the other side you have an anode, right? If you remember what cathode and anode mean. And I'm not trying to tell you that this is the right direction, but I could have a ground. All right, so I got a ground, and internally that ground would be hooked up to the negative side of the diodes. And so now my grounds are, it would be better if I did that in green, I know. And then I could turn these guys on. So if I wanted a 0, I want that, and then I'd have a 0. That's an 8. 0, that's better. And the segments are A, B, C, D, E, F, G goes across there. And then there's dots, because I could put dots in too, right? So I could have a right dot and a left dot. So in case I wanted to put a dot in there. And or I could make them so that they're a common anode. Yeah, a common anode. And I could bring in positive. That was dumb. So I could bring in 5 volts. and have my 5 volts hooked up to one side, and then bring my signal in to the other side. Boy, am I making that messy now. Okay, so I could bring the 5 volts in, and then ground what I wanted to turn on. So I could use that situation too. And if you remember in your TTL logic earlier in the book, we said that TTL logic can't give very much power. So TTL logic isn't going to turn on these guys, but it will ground them so that they come on. So the NOT will sink enough power to turn on a segment of the 7-segment display, but a buffer will not send enough power to turn it on. Okay, so that's just one of those things. And on page 571, we see that that's what we're doing. We're putting 5 volts in, and we're using a current limiting resistor to get the 10 milliamps that we're looking for, and so we don't burn it up as well. All right, well, in order to do it, we're going to have something to do it with. So we need a decoder. And somewhere in the labs, you're going to start using this decoder. So we have a 7447 TTL chip, and we have binary coded decimal coming into it, and we have 7-segment display coming out, 1, 2, 3, 4, 5, 6, 7, and they're knotted outputs, so that my current is going to be flowing that way into the chip and be synced by the chip. I'm going to have a bunch of 330 ohm resistors in there too, to make sure I limit my current. And then I can go and have a group of these guys. So I'm going to have 1, 2, 3. I'll do 4. You like 4? Yeah, 4 will do. Take too long to draw more. Have 4 of them, and then have some circuitry, some timing circuitry that turns them on one at a time, and then have an address bus, a data bus. Data bus. That doesn't look like a bus to me. I just can't imagine. So I have a data bus going into each of these guys, and then as I choose them, they come on. And as long as I turn them on faster than 17 hertz, you're going to think they're on continuously. So 100 times a second, I can have them cycling through this, and you're going to think they're on continuously. You're not going to see that flash at all. And that's how I would make that work. Look on page 575, and we see such a circuit that's doing that. Well, better yet, look at 576, and we see whatever it is.
6. I didn't see in the book where you got the 4.
Get what?
You get your 4 LEDs there.
Well, now on page 576, I got 1, 2, 3, 4, 5, 6 of them. Yeah. But I'm doing the same thing. I've got a data bus going to all of them, but then I'm only selecting one at a time to turn on. So that's what I'm trying to display here in my own silly way. And then 575, we see what my truth table is for the 7-segment display. So that's pretty good. And it's not A, not B, not C, not D, not E, because they're inverted outputs. So that's why that N is there for the A in that. Okay. You also have 3 control lines coming into your control. going into your 7440 is the decoder, not the inverter. But that decoder has inverted outputs.
Okay.
Yeah. So the inverters are part of the decoder. You don't have to put other things on. All right, now we're in 12.7, and we're thinking about synchronous counters. And look at this. While looking at synchronous, the instructor can spell it properly. Maybe. Look at that. I spelled it right for the first time this semester. And synchronous counters mean I have something with a clock. And that all the flip-flops, so I have flip-flops, there's one, there's another one, we'll only have two, but all the flip-flops are controlled by the same clock signal. And that's what makes the counter synchronous. So on page 580, what do we see? We see something that is counting up. How do I know it's counting up? Well, I'm looking at the output that's there. And so if I make my inputs, oh, no, I'm not counting. Well, I'm doing something weird here, aren't I? I'm doing more than just counting up. Looks like I'm counting up though. Yeah. 4-bit mod 16 synchronous counter output waveform. Yep, that's what I got. And then on page 581, looks like we're doing something else weird. I wonder what we're doing there. Oh, we got a mod 6 counter going 0, 1, 2, 3, 4, 5. So when I get to 5, I end up resetting. So, you know, on the right-hand side there, you see where I've got an AND gate that has the most significant bit and the second most bit in it. Well, when I get to 5, 5 looks like that, right? So this wouldn't turn on. When I go to 6, it looks like that. Now this guy turns on, and when he turns on, it resets the counter back to 0. So as soon as I get to 6, I immediately go to 0. And then I've got myself a manual reset switch too if I wanted to use it. I look on page 582, system design for a hours of darkness counter. Okay, well that's cool. I've got some light emitting receiving photocell here that's going to turn on when the sun's on. When the sun comes on, then my counter counts. Isn't that special? I'm sure that we all want to know that, right? How many hours of sunshine there is every day. Well, if I was a wind technology guy and I had a photoelectric cell panel on top of my house, I might want to know how much sunlight I had. Maybe. Okay, looking at 12-8, we have a up-down counter. So I'm using the same counter. I can go up, I can go down, and I do it whether or not I tell it to count up or count down. So this is a 74, 129, 192, 193, two different ones. Not sure what they do, different, but they can either count up or count down depending on whether or not you tell them to count up or count down. And you can change the direction at any time. Just, I'm counting up now, and now I'm going to count down. Now I'm going to count up. Now I'm going to count down. Sort of like, the Huskers when they play football. You never need to count up on the score. Speaking of football, and I know you're all interested, Iowa Western went 0-2 for the season, went from ranked second in the country preseason to unranked. Now they're 7-2. They won the last 7 games in a row. Compared to the another team that's close by, whose name won't be mentioned, but their initials are H, and what are they, about 0-7 now, something like that, 2-7, whatever they are. I'm not sure what they are, but for whatever reason, our coaches,
Five is what you're looking for.
oh, they are?
Yeah.
Oh, I wouldn't know that,
Let's
but
put that up there
yeah,
for
3
video.
and 5 for the video, some other team,
Yeah.
3 and 5. Whereas Iowa Western, IWCC is moving up in the polls. We're still in the double digits ranking right now. We're like 11th or 12th. And
But they play
we will play a bowl
They probably play
game.
a similar schedule too.
Yeah, they probably play. Yeah, we play hard teams too. And before you joined the program, the other team, the other unmentioned team that wears red, was looking for a new coach. Right? You remember that? And the joke was on campus is that they shouldn't look for a new coach. They should just go to Iowa Western and hire the entire coaching staff. They'd be much better off. And there's some thought to that, yeah. Because clearly, now we lost the 2 games because our quarterback was hurt. So our quarterback got hurt, collarbone injury before the first half of the first game, and but he came back and now he's back. Some guy from Omaha North. So our quarterback's from Omaha North, and why isn't he playing for the team that's in red? It would seem like if we had a good quarterback from Omaha North, he should be someplace else. It would seem that, but no, doesn't work that way. Anyway, so now we talked about football. Up counters, down counters. Synchronous counting ICs, applications of synchronous counting ICs, doing it in computer programming. Good thing we're not doing that. I'd have to learn something new. That'd be really bad. Paul decided in the first semester here he would do all this VHDL stuff, and it was a disaster, total disaster. Okay, back to page 606. We have a thing called a state diagram. And this is just a computer programming tool. If I'm in a particular state, let's say I'm in the 0 state here, where do I want to go next? I don't know. Wherever it is, I have to go next. I have to go there next. So for the sake of argument, we'll just go to 5. For whatever reason, whatever 5 is. And then from 5, we'll go to a 4. Yeah, we'll go to 4. And then we'll go to, what do you want to go to next? 7. Then we'll go to 7, then we'll go back to 1, to 0. And then we'll do it again. For some reason, whatever, it doesn't matter what the state is. You make a state diagram to help write the computer program later. I'm going to go from one place to the other place to the other place. All right, so now we're going to implement the state program. And we're going to do that with flip-flops. How many do I need? I'm going to need 3 flip-flops because I'm going to need 3 significant digits. Okay, so I have 3 flip-flops. So 1, 2, 3. So I got 3 flip-flops, and so I got J and K on that one. I got J and K on this one. I got J and K on that one. And then we remember that if I'm at 0 on a flip-flop and I want to go to 1, then that's a 1 I don't care on the JK. Because if it's 1 0 I've set, if it's 1 1 I do a toggle and I get there. If I'm 0 and I want to go to 0, then that's going to be a 0 I don't care. Because a 0 0 is a hold and a 0 1 is a reset. If I'm at 1 and I want to go to 0, then I'm going to need a I don't care 1. 0 1 gets me a reset. 1 1 toggles to 0. If I'm 1 and I want to go to 1, then,
You're not tired, 'cause you got
Battery is fine.
oh, bad.